This is a short lecture consisting of only 4 slides. The purpose of the lecture is to bring attention to the important steps and concepts that we use to derive the shallow water equation, to explain planetary scale waves in a stratified rotating atmosphere. So to begin with, before we start deriving the equations, we like to inform you why we can do this. From a P set of equations for the stratified atmosphere, we can apply the concept of normal mode decomposition to derive the kind of mathematical set of equations that's equivalent to the shallow water equation. Okay, so the left-hand side shows the P equations that consisting of the horizontal momentum equation. Okay, that's the acceleration term, the Coriolis term, and the pressure gradient force. Note that this is already linearized with the rest mean state. That means the basic flow is 0. Okay, we'll only consider the perturbation, the wave motion. So all the variables are shown with prime. That means perturbation. So for the horizontal momentum equation, you have u prime, v prime, and phi prime. The phi is geopotential height. And then you have the continuity equation. Okay, and then the thermodynamic equation in the hydrostatic system, because we're dealing with planetary scale waves. So we don't need to worry about the vertical momentum equation. Instead, we are working on a hydrostatic system, and this we will show in the next few slides. You can derive this in the shallow water equation. Okay, in the stratified atmosphere, the linearized, inviscid, and the rest mean state condition, you can write down this set of equations, and then you can apply the normal mode decomposition by expressing the u prime, v prime, phi prime, and omega prime that are functions of x, y, p, and t as the horizontal part of the variables that is expressed by u, v, phi, and omega, which are function x, y only, and of course t. And then in the vertical dependence, for example, for the omega prime, that is expressed by the horizontal part and the vertical parts. Okay, so this is a normal mode decomposition. We assume the variables, all the 4 variables can be separated between the horizontal and the vertical structure. Okay, so this is very important treatment of these variables. Okay, and then the reason for omega, you have the horizontal part and the vertical part. But for the u, v, and the phi, the vertical part, which is the vertical derivative of the w. Okay, so this you can see from the equation, the u, v, and the phi, they are the balance force, the pressure gradient force, Coriolis force, okay, balanced with the inertial term. Okay, so this has no vertical dependence in the horizontal momentum equation. Okay, but in the continuity equation, the horizontal momentum is balanced with the vertical derivative of omega. Okay, so for the horizontal momentum equation, for the horizontal winds, the vertical structure has has a derivative, is balanced with the vertical derivative for the omega. So that's the reason you want to express the vertical dependence part by W and the dW dP for the moment, for the UV and omega. Okay, and also for the thermodynamic equation, again, the thickness d phi dp, normally we call that thickness. Okay, that's dependence. That's in the hydrostatic system. That's proportional to temperature. Okay, so the omega and the d phi dp have the same vertical structure equation. Okay, so that's why the phi also has the dw dp vertical dependence. Okay. Once you make this separation between horizontal and vertical component, then you can substitute this into the P equations, and then you can obtain the horizontal part. Okay, here the horizontal momentum and the continuity and the horizontal momentum equation, the two U and V momentum equations are function of x, y only. There's no dependence in P. Okay, and then the dependence in P here comes from the thermodynamic equations. Okay, in the thermodynamic equations, you have a W and a phi T. Okay, and then with separation of variables, you can obtain two equations. One is this part. Okay, and this part gives you this continuity equation. Okay, and this part that is becoming the second partial, the differential equation, second order differential equation for W in P. Okay, so with the separation constant C here. Okay, so you can then solve this second order differential equation in P, and then obtain with proper boundary condition, you can obtain the eigenvalue as function of the separation constant as an eigenvalue. Okay, in this form. So that means for each m you have a separation constant, and that corresponding to in this way. This looks like actually this is come from the thermodynamic equation, but in the shallow water equation that you will see that actually is related to mass continuity equation. Okay, so this is actually equivalent to the thermodynamic equation. Okay, so this is a very important part, that the concept vertical mode decomposition that we applied, that give you a shallow water equation that is we can derive from the water equation in the following three slides. In the mathematical form, it is equivalent to the P equations. Okay, so here this set of equations derived from the P equation, and it consisting of different linear combination of vertical modes. For each vertical modes, the accompanied horizontal structure bears the same mathematical form as the shallow water equation. So if we can start from shallow water equation, we can obtain the wave solution rather easily, and then that can be applied to the stratified atmosphere. So normally we pay more attention to m equal to 1, so-called first baroclinic mode. Okay, and m to 2 becomes second baroclinic mode. For each mode, m equal to 1 or 2, we have a set of equations that have the same form of shallow water equation, but with different separation constant Cm. Okay, the physical mean of Cm is actually in the shallow water equation is the gravity wave speed, and here it's called equivalent depths, because c squared in the gravity wave equal to square gh. H is the water depth. So cm in the atmospheric baryclinic mode, we call the equivalent depth. Okay. For the next few slides, we follow Pedolowski's textbook, Chapter 3. It gives you a very systematic approach to derive approximate set of equations for the shallow waters. Okay, so this is the rotating coordinate for the shallow water. Okay, so the shallow water has constant density, okay, and with viscosity equal to 0, it is rotating, and with the characteristic horizontal length scale L and the vertical length scale D, okay, the depth of the water is H. Here it has a lower topography like in the ocean. Okay, you can have a low topography. Okay, in the I think when you read like chapter 3 of the textbook, you may not need to worry about this lower topography. Just set HB equal to 0 would be okay. Okay, in this case, so-called shallow water waves means that the length scale of the wave has a much longer horizontal scales than the vertical scales. Okay, so that's the definition for shallow water. That means we're dealing with long horizontal waves. Okay, so practically in the atmosphere or ocean, the horizontal scale of wave what we are interested is of order of 1,000 kilometers, while the vertical length scale is about 10-20 kilometers. So the aspect ratio of D over L is much, much smaller than 1. Okay, so for the shallow water, the original water equation is written on the left-hand side. This is continuity equation, the zonal momentum equation, Mariano momentum equation, and the vertical momentum equations. Okay, and then in the textbooks, it gives a systematic approximation. Here I only highlight the important steps. First, from the continuity equation, you can express this continuity equation by a dimension, like du dx can be expressed by the characteristic velocity v u here, okay, and by divided by x, we use L as a characteristic horizontal length scale. The same thing, dv dy can be expressed as u over L, and dw dz can be expressed as w over d. D is the vertical length scale. Then you can show very easily that the vertical velocity should be smaller than the horizontal velocity times the delta. Delta is the aspect ratio, or the D over L, which is much smaller than 1. So this indicates for the large scale waves, the vertical velocity is much smaller than the horizontal velocity from this simple dimensional argument. And this has a very important implication, because from this scale argument, then you can, from the vertical momentum equation, you can show that actually the vertical momentum equation is actually a hydrostatic in hydrostatic balance. So that means you don't need to worry about the vertical momentum equation at all. Just the hydrostatic relation replaces the vertical momentum equation. And from the hydrostatic equation, you can then obtain P as function of Z. Okay, so the pressure is determining the depth of the water. Okay, and then the horizontal pressure gradient can be expressed by the horizontal gradient, the depth of the water. Okay, so this is a very important steps. Once you have this pressure gradient expression, so you can see right away the horizontal pressure gradient is independent of z. Okay, because h, the depth of the water, is a function of x, y only. Okay, it does not change with height. Okay, so therefore the horizontal accelerations must be independent of z, because the horizontal pressure gradient is an important force for determining the horizontal momentum acceleration in the horizontal momentum equations. Okay, so if the motion or the velocity, horizontal velocity, is initially zero or initially z independent, then the horizontal velocity themselves will remain independent of height. Okay, so this is a very important step, because this right away you can neglect the vertical variation of horizontal momentum. Okay, so the vertical momentum advection is, you can neglect it. Okay, in the horizontal momentum equation. And also, because now the velocity is independent of z, so then you can integrate the continuity equation, because du, dx, and dv, dy will be independent of z. So you can easily integrate this equation to obtain w, the vertical velocity, okay, from the continuity equation. Note that this w is not derived from the momentum equation, but it derived from the mass continuity. So this is actually a diagnostic w, okay, and this w with appropriate upper and lower boundary condition, you can derive this mass continuity equation. This is very intuitively simple. That means the horizontal convergence of the water will determine the depth of the water. Okay, so this is, if HB is 0, then this is quite straightforward. Okay, so this is the set of equation for the water. From the water equation for the large scale waves, you can derive this z independent momentum equation and mass continuity equation, and then you can assuming the small perturbation, you can then easily neglect with no mean state, that if the mean motion is rest, then the advection term, the nonlinear advection term, becomes second order. Okay, you can neglect them too. So you get a linearized momentum equation as this. So this is the same as the shallow water equation that derived from the PE equation set. Okay, so that's why we can start from the shallow water equation to study the waves in the stratified atmosphere. Okay, so for the shallow water equation, you have three variables, u, v, and eta. Eta is anomalous thickness from the thickness of the fluid layer in the absence of motion. So if there's no lower topography, this reference height is actually constant in x and y. Okay, so this is simply the anomaly in the depth of the water. Okay, so when the wave oscillate in this shallow water system. Okay, so this is a very simple set of linear differential equations for three variables. So with appropriate the derivation, for example, you can combine these three equations to obtain a high order differential equation for eta. Okay, once you obtain eta, then you can substitute into U and V to obtain U and V. So, so it is possible to obtain analytic solution from this set of linearized equations. Okay, so these are the important steps and concepts that you need to understand when you read the lecture notes. The chapter 3 in Pedalowski's paper that gives you a more detailed description of the derivation. I think this is very important. Okay, so the shallow water equation is an approximate set of equations for you to understand the large scale waves. Okay, and from this simple set of equations, we are able to derive analytical solutions, as what we'll do in the next few lectures. Okay, so you can obtain the analytical solutions. You can express the solution from these mathematical forms, then you can understand the type of wave motions in the atmosphere and also in the upper ocean as well. Okay, so this is a very important mathematical set of equations or approximate set of equations for describing the large scale wave. Okay, so I hope you can follow these important steps and concepts when you read the lectures. Okay, so we can have, you can ask me questions when you have any problems. We'll stop here for these short lectures.